Okay. So here we go with lecture number 4. And I know that many of you have been asking what's the status of the kits. So let me tell you what the situation is with those. Okay. You should have my slides up there. So we're building kits for you that look like this. It's a box that you can carry around easily, and it has in it an Arduino Uno as well as a bare at Mega 328p chip, and then breadboards, cables, wall warts, all kinds of things like that that'll allow you to program it at different levels. Now, this kit actually has in it about 100 pieces in it. Many of the small pieces are in this little bag up top. But when you add it all up, it's about 100 pieces. And we're building 300 of these. We need 300 of these for both this class and ECE 304, Junior Design Project. We've been dealing for months with a vendor who was going to get us these, and just about 2 weeks ago, we learned from them that they won't be able to deliver the kits to us until mid-April. Well, obviously, that's too late for us. So we said, okay, go ahead and ship us all the components. So they shipped us several tens of thousands of components, and we're now assembling those in the lab right now for you. And so we've set up an assembly station in there, and the teaching team is setting about building all these kits for you. Once we have all the pieces in little bags, and we put those into the bigger kits, and then we'll have them available to you. And I aim to get these to you by the end of this week. And if not that, then on Monday, beginning of next week, so that we can then get on with this part of the course, that is the embedded part of the course. Now, I should add, this hasn't been holding us up at all, because the stuff that we're doing now is still based on learning C. We're not yet at the point where we need these things, but I know you're anxious to get them in your hands, and I've been telling you they're coming. So end of the week is when I expect to have those available. Okay. Sort of a couple of announcements. That was the first one. The next one, we're based on the last 2 lectures, I'm getting a good number of questions, both in class and in chat, which is fine. Keep them coming. I just want you to know that another source of information for you is to go to Piazza. Only about 1/3 of you have actually signed up to use Piazza. If you look at the very first slide in L3, right now we're working on L3, lecture 3, but the very beginning there, it gives you the URL that you can go and sign up for Piazza. You go there, you got any question, you pose a question, you'll get an answer fairly quickly. Moreover, you'll be able to go there and you can see all the other questions that have been posed and answered, and it's an excellent resource that you'll find helpful as we go along through the course. So if you haven't done so already, I urge you to sign up to use Piazza, okay? The next thing that I want to announce to you is that you saw an announcement from me last week telling you that an alternative to using the C compiler on Windows or on Mac for this part of the course, for this first 2 weeks of the course for lab assignment 1, an alternative to downloading a compiler and all that is to use an online C, really it's an emulator. It's very simple. You don't have to download anything. You can just go right online, type your code in, and get an immediate result. And check the announcements from me last week where I gave you the URL from that. I'm using that in a number of the demos that I'm showing today and also on Wednesday. And this will be helpful to you now if you want to use this instead of using CLang or the MinGW 64 compiler. Now, if you've already got those compilers working on your machine and you're comfortable with them, great. The reason why I made this change is for some people, when you're trying to install CLang, which is the GCC compiler for Mac, you have to install 20 gigabytes worth of bloatware. I didn't have to do that when I tested it. It was really an order of magnitude less than that. But some of you are finding that just to download that compiler, you have to go and install this whole big thing associated with Xcode. I don't know why that's a requirement that Apple is putting on that compiler set of tools, but it is. So the workaround is to just use that online compiler. Very simple. Okay, we will though, once we start to get into programming chips, then there is another compiler that you're going to have to use, AVR GCC. Next week, I'll be giving you the instructions on how to do that. Okay, just one more announcement-y kind of thing. I am recording all of the classes, the Zoom lectures, and then making them available after class. So it's perfectly okay if you want to participate in the class there in the room, as many of you are, or if you want to participate via Zoom right now from wherever you happen to be. Either of those is a perfectly acceptable way of participating in the class. And I recognize that a number of you, for one reason or another, can't or don't want to actually be in the room, whether it's because you're commuting or you're, or perhaps you're quarantining or someone in your family or whatever the reason. So we make Zoom available. So either is a perfectly valid way of participating in the class. And moreover, if you choose to participate asynchronously, that is, instead of watching this lecture now, either in class or via Zoom, if you want to watch it later on, that's okay too. Any of those are fine. I do strongly encourage you to listen to all the classes because you're getting information here that this is just how I convey it to you, and if you don't view the lectures, you're missing out on stuff you got to know. Okay, that's it for all those announcements. So let's pick it up where we were last time, and we were in L3, lecture notes 3. And I did hear from some of you, you would prefer, what you're doing is you're following along with a PowerPoint, not PowerPoint, with a PDF deck. And you're using PDF because you can annotate that more easily in class. And so you asked if I stopped doing animation builds because, with an animation build with PowerPoint, you can sort of see all the animation developing. If you do that onto PDF, it all sort of everything gets posted onto one slide and the stuff underneath is buried. So I have expanded all the slides, and I'll do that going forward so that I won't have animations. Instead, everything will be on a single slide. Okay, so with that, let's get to it. And here's where we were. And we're talking about the data types in C. And where we left it last time, just to sort of back it up, is I told you that there's this sort of, initially anyway, a sort of a bewildering variation of integer data types. You can have an integer means you don't have a decimal point, right? And so they can be signed and they can be unsigned. They can be short, they can be long. These are all different ways of specifying an integer. And I wanted to just connect that with how much memory these things take. So we showed you this slide last week, and we left it at this. If you have an 8 bits, if you're dealing with a memory cell that's 8 bits wide, 1 byte wide, well, you can represent 256 different things with that 8 bits, because 2 to the 8th is 256. And so if we decide that those 8 bits are going to be used to represent an unsigned number, that means it's a positive number only, then those numbers can go between 0 and 255. On the other hand, if we say, well, we want to represent both positive and negative numbers, well, one thing we can do is we can take one of the bits and use that as a sign bit. If that bit is 1, perhaps the number is negative, and if it's 0, the number is positive. Then that leaves only 7 bits for the magnitude. So that means if we have signed values that are represented with 1 byte of memory, then they can occupy from, well, if we just went with this sign magnitude form, if we just used 1 bit for the sign bit, they would go from -127 to +127, and we'd have 2 different values for 0. It's not quite how it's done. 2's complement representation does it a little differently. We don't need to look under the hood at that. But the point is, if you have 1 byte, you can either use that to represent unsigned numbers between 0 and 255, or signed numbers between -128 and 127. Okay, and now suppose that we're dealing with integers and we want to go beyond 1 byte of storage, right? So let's suppose that this is what we just talked about. If you have 1 byte, signed or unsigned, but if you have 2 bytes, right? If you want to allocate 2 bytes worth of memory to one variable, 2 bytes is 16 bits. 2 to the 16th is 65,656, I think. 65,536. I think that's right. And if they're signed, then it's -32,768 to +32,767. If it's unsigned, it's 0 to 65,535. Yeah, this should actually be a 5, not a 6. It's not crucial for us right now. Okay, suppose that we want to have a data type that can represent even bigger numbers, right? If we use 4 bytes, 32 bits, then 2 to the 32 is this huge number, right? It's 4.3 billion. And if we go to 8 bytes, meaning we're allocating 64 bits for a word, 8 bytes, right? Then these enormous numbers. So we can represent, they're all ints, but we can represent different size integers by allocating different amounts of memory to the different data types. And so here's a list of all what we think of as the standard data types just for integers. There's char, which is the smallest, and then that can be signed or unsigned. There's short int, and that can be signed or unsigned. There's a int, and that can be signed and unsigned. And there's also a long, right? There's a whole bunch of these. And why do we care about this? Because the different widths of these in bytes will specify different minimum and maximum values. So why don't we just always use really big ones? And that way we can always have enough space to represent, whatever the biggest numbers we can possibly be using. Well, if you were programming in an environment where you have endless memory, that would be fine. But if you're programming on a little chip that only has a few kilobytes of RAM, then this matters. So let's suppose, for example, we're going to be working with an array, and we'll define an array more formally on Wednesday. But suppose that and you've seen arrays previously in programming. Suppose we want to keep track of an array of 1,000 temperature values. And suppose we want to define them as longs. Right? It means that it's whatever the data width of longs would be, right? Well, that would occupy, if it's 1,000 longs and they're 8 bytes wide, then you'd need 8 kilobytes of memory to represent that. If, on the other hand, those temperatures were smaller numbers and we represented them with shorts, then that would only be one kilobyte. So it's a factor of 8. Okay. Now, if you're programming on your laptop and you have gigabytes of RAM, you don't care about this, probably for this particular case. But if you're programming on that Mega 328p chip that you buy for $2, and you only have 2 kilobytes of RAM for your entire program that you're going to write, then these kinds of things matter. Okay. Now, where this gets a little tricky is different compilers are free to choose how many bytes they want to allocate for these different integer data types. So on one compiler, int may be 2 bytes. On another compiler, int might be 4 bytes. So the next series of slides goes way down deep. It goes down the rabbit hole in sort of describing all this using one of the keywords called Sizeof. And you can use Sizeof to ask the compiler to tell you how many bytes does a particular data type occupy. So I just wanted to show you briefly this. I'm only going to show you some of the information here. The rest of it is there for your reference if you want it. So here's a little program. And what's it doing? It's going to demonstrate the use of the Sizeof keyword to determine the width in bytes of a variable, a literal, or a data type. Okay. Now, I presume at this point, you're following along with your laptop. We're on slide 39. The font is small, but if your laptop is in front of you, then you can see this just fine. And this is how I'll be doing these all these slides going forward. So let's look at the code here. So we're just going to use this keyword Sizeof to determine the width in bytes of some different objects. So what is the code? I have int x, I'm just declaring an integer, and then I'm doing 3 different prints. Now, we haven't looked in detail at this printf function. I'm going to do that next. But for now, let's just sort of look at these examples and just see what this gives us. Okay. What I'm going to do is I'm going to say variable x is, and I'm using size of x. It's going to tell me how many bytes wide x, the variable x is, right? Then I'm also going to do this. I'm looking at the size of int. So I'm going to find out the size in bytes of the integer data type. And I'm also going to have it tell us what is the size of the number 50. That's a literal. So I'll just go to the next slide and it'll give us the result. Variable x is 4 bytes wide. I declared x as an int, it's 4 bytes wide. Type int is 4 bytes wide. Literal 50 is 4 bytes wide. So that tells you if you're just working with your plain old garden variety integer data type int, on this compiler, it's 4 bytes wide. Okay?
Professor, we have a question.
Go ahead.
No, it's good. It wasn't popping up on the screen at first, but now it is.
Okay. Never mind.
Say again now?
Yeah.
It's all good now.
It's all good. Okay. 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 Now the next slide, just for your information, I'm gonna put these here. The details are here if you want them. But what I've done here is I'm using that Sizeof function and some other things to go and compare the width of different variables: int, unsigned int, short int, long, float, double, char, all these kinds of things. I'm comparing those on different compilers. And I'm just going to sort of show you kind of some punchlines here. So first what I'm showing, okay, someone asked, what is LU in a print statement? We'll get to that, Harry. We'll get to that in a bit. The LU is just a format specifier in a printf statement. We'll get to that. But here, what I've done is I've run some code on 2 different compilers. On the MinGW64 compiler, which most of you are currently using because you have a Windows machine, and then the CLang compiler on the right. That's if you're running Mac. And it's just telling, all we wanted to ask is, for different data types, how many bytes are allocated? And so you can see for type int, they're both allocating 4 bytes, okay? But if you look at long int, one of those compilers allocates 4 bytes, the other one is allocating 8 bytes. So that's interesting. If you look at float, this is where, if you care about a decimal point, 4 bytes on one compiler, okay? Type double is 8 on both. Long double, this would be a double precision, long double precision. This would be a number that has an awful lot of bytes associated with it to get a very high precision in representing a floating point number. On the Windows machine, it's 16 bytes wide, and on the Mac machine, it's 8 bytes wide. Don't for an instant try to memorize this, right? Don't just observe that some of these are common between the 2 compilers and some are different. That's the only thing I want you to take away from this. Okay, now I'm going to show you what it looks like on the compiler we'll start using next week. This will be the AVR GCC compiler, which is the compiler we'll use to compile code on one of your machines so that it is then rendered as a binary executable on your microcontroller. Type int is 2 bytes wide. So these others were 4 bytes wide. Type int is 2 bytes wide. Okay. Type float is 4 bytes wide. Type double is 4 bytes wide. Type long double is 4 bytes wide. So they're different, right? So different compilers have the right, have the freedom per the C ANSI standard to interpret the width of the spec in different ways. So different compilers are free to assign different widths to these different standard data types. That can be confusing. So if you're unsure, you can always use the function Sizeof to find out how many bytes is allocated to a particular data type. But what I'm going to do here is sort of roll all of this up into this slide right here, slide 53. This is relevant not for your the compilers you're using right now, whether it's Mac CLang, or Windows, you're using MinGW64, you would use both of those if you're programming in the large. You're writing some C program, building an operating system, you're building something that's going to run on that computer. You got plenty of RAM. You got 16 gigabytes of RAM, right? That's not what this is about. This tells you the data types that are associated. And this is from the textbook that we have for the class. And we'll start to get into that book next week, but it's on page 225. This tells you specifically for the AVR GCC compiler, what are the size in bits of the different data types, and then the corresponding range, the minimum and maximum values of different numbers you can use. And this matters because we're going to tend to want to conserve memory when we're writing code on one of these chips, because again, there's only a couple of kilobytes of RAM to work with. This is just something to be aware of. Sort of tuck it away. We'll make use of it later on when we need to. Okay. I just want you to be aware that in addition to what we call the standard data types, right? What's listed here are the standard data types. They just come with all the compilers. There's char, signed and unsigned. There's int, signed and unsigned. There's long, there's float, there's double, right? Oh, and by the way, the ones up top here, these are all the integers, right? Where you don't have a decimal point. And then if you are working with numbers where you care about the decimal point, these are the two types you would use on our microcontroller, float and double. Float represents floating point, double represents double precision. But note, the values are the same here. So the double precision data type has the same width and hence the same precision as the floating point data type on our microcontroller. More on that later on. Okay, there's a keyword called Typedef, and what that allows you to do is actually declare new data types. So char, int, long, float, double, these are intrinsic data types. They're built in to the particular installation of C that you have. You can also create your own data types if you want to. So for example, if I were to write type int myInt, what I've just done is I've just declared that myInt is a new data type, and it has all the characteristics of int. So if here I have, I'm doing a declaration, myInt a comma b. I'm declaring two variables, a and b. Each one is of type int. Okay, here's another example. Typedef, unsigned int myShort, and then myShort AB. I've declared a new data type, myShort. So we have intrinsic data types, int, long, float, double, intrinsic to the particular compiler you're working with. Here is new data types that you have the freedom to create using Typedef, right? We're talking about data types. So here it says type definition. We're defining a data type. We're defining a data type called myShort that has the characteristics of unsigned int. Now, why would you do that? It won't be obvious to you why you would do it at this point. But I just want you to know that all the compilers actually define, using Typedef, something called the fixed width integer types. Now, this is when you first look at this, you're undoubtedly going to go, huh? How does that work? Okay, look at this. This is a data type, int 8 underscore t. And here's another one, u int 8 underscore t. Both of these are 8-bit data types, meaning they'll occupy 1 byte of memory. The difference is the one that begins with u is unsigned. The one that doesn't have the u is signed. So both of those are data types that will only occupy 1 byte of information, right? So you have, they're defined using Typedef. They come with the library associated with your C installation. And this won't be apparent to you now, but we'll have occasion to use these later on when we want to be sort of sure that we're specifying a data type that's either 8 bits or 16 bits or 32 or some other value. Okay. Okay. So just a little bit more about this. If we were using AVR GCC, that's the compiler we're going to start using next week. Why is it called AVR GCC? AVR is the processor used in the microcontroller we're going to be working with next week. It's the Atmega 328P that has an AVR processor inside it. And so AVR GCC is the compiler you use for that family of processors. And I just wanted to show you a little bit of some memory mapping here. Suppose that I I want to declare a variable C, and I'm going to, it's type char. We'll say more about this. We may get to this today, but I'm just declaring it as one character, right? I would declare it. I could declare it like this: char variable name C, and it's equal to the letter A, or char only occupies 8 bits, so I can declare it using what I just previously showed you, this fixed 8-bit integer data type C. And the point is, it will occupy each of these memory elements represents 1 byte or 8 bits. On the other hand, suppose I wanted to declare a variable A1, and I want to give it a value 255. An int, I'm going to back it up. How much data did an int take up on this compiler? I'm going to back up 1, 2, 3, 4. Okay, an int is 16 bits. So an int is 16 bits or 2 bytes. So an int is going to take up 2 bytes of memory here. Okay, and here I'm declaring a variable A1 of type int, and I'm giving it the value of 255. So that 255 would be stored in these 2 bytes as a pattern of 1s and 0s. Okay. All right. Suppose I wanted to have a variable of type long, and the variable name is lng. That's going to occupy 4 bytes of memory. Okay, and so on. So I just wanted to give you some idea that when we declare a variable and initialize it to a particular variable, memory then gets allocated for that variable, and the particular value gets represented as a pattern of 1s and 0s inside memory. And again, I've said it before, I'll say it again. The little microcontrollers we're working with only have 2 kilobytes of RAM to work with. So your program, the flash ROM, the size of the program can be up to 32 kilobytes, but the RAM itself, that is the variables in the program, can only occupy 2K. More on that later. Okay, so let's just sort of do a little exercise here. Suppose that we wanted to be really lean. We wanted to conserve memory. So I want to use the most compact data type available to me. So suppose that I have a loop, and we'll talk about loops in a little bit, but you've seen loops before, for loops, while loops. You've seen them in Python and other languages. So, but suppose we have a loop variable and it's counting from 1 to 100. Well, what kind of a data type should we use to represent that? Well, we could use, if it's between 1 and 100, then it's unsigned. So we don't need to go negative. We could use an unsigned char. That's the smallest data type. It only occupies 1 byte of information. Or we could use what I just showed you briefly, and probably confusingly, this thing called an unsigned 8-bit integer. It just occupies 1 byte of information. Okay, but what about the number of people in a classroom? What kind of a data type should we use to represent that? Well, it depends on the class, right? This class has got about 150 students. So if it's less than 255, we could get by with 1 byte. So we would use the unsigned char data type, right? But if we had more than 255 students in the class, we would have to go up to 16 bits, and we could use the unsigned int. Okay, and I'm doing something that you wouldn't do on a big computer with plenty of memory, but it's the kind of stuff that we'll be doing starting next week. All right, a person's body temperature. When you go to see a doctor, they take your temperature, right? You go into I've been in furniture stores where they take my temperature when I walk in nowadays, okay? What kind of a data type do we need for that? Well, your temperature, 98.6, right? 100.2, there's a decimal point there. So to keep track of a body temperature, something like that, where we care about the decimal point and fractions of a degree, we would use the floating point or float data type, and that would occupy 4 bytes. All right, a person's age in years. Well, someone's age in years is going to be a number between, it's going to be a positive number between 0 and, well, 100 and something maybe, right? But it's going to be less than 255. So you'd use the unsigned char data type for that. All right, what about a person's age in seconds? Well, how big can this be? So let's suppose that someone, how big a number could be. If someone is 100 years old, how many seconds is that? Well, here I typed it up. It's 3 million something seconds in 100 years. So we need to use this bigger data type to represent that. So I just wanted to show you that depending on the application, you can choose different data types. And if what you're trying to do is conserve memory, then what you want to tend to do is ask, okay, what are the range of values that this variable might contain? And then let me choose the smallest data type available. And we'll cover this in more detail once we get into this using the actual chips. Okay, finally, let's get to this printf stuff and see what are all these funny characters in printf. So printf is not a keyword. Printf is a library function. And so, we've got the list of C keywords. It's a relatively small number, right? Those are the actual words that C understands. Int, void, do, for. We'll see some of these coming up next. But printf's not one of those keywords. So printf is a library function. It's a function that someone else made, and it exists. It's part of the standard C library that comes with your installation of C. And so the way that function works is you call it and you give it a bunch of arguments, right? Argument 1, argument 2, and so forth. And so as an example, this is what I've been using the printf statement a lot, and it kind of looks like this. Right, it starts out with some things in quotes, right? Quote, some text, and then I have this parenthesis X, maybe some more text, parenthesis Y, and then I might have a couple of arguments out here, let's say thing X and thing Y. So what's happening there? That parenthesis, that percent sign there, that's percent. That's called an escape character. Okay, now here's what happens. Here's how this works. This is a format specifier. Okay, the printf is called formatted print. And what it allows you to do is print something to the screen or to a file. Soon we'll be seeing how we can print stuff onto one of these little tiny organic LED displays, right? But you can print it in a way that's formatted. And parenthesis X is a format specifier. And the first format specifier modifies or describes how thing X will be printed. The next one will describe how thing Y will be printed, okay? And the idea here is when you set up a print statement, you'll first have this stuff between quotes, some text you want printed, and then the format specifiers. And %X specifies how you want thing X to be printed. Is thing X going to be printed as an int, as a float? If it's a float, how many decimal points of precision do you want? And these things have to agree. If you try to print an int as a float or as a string, you're going to get a compiler error. Okay, so the idea is that these things have to match up. They have to agree. And now here we have down here is just sort of the laundry list of different specifiers. If you want to print an integer, an int, as a signed decimal number, we typically use D. If you want to print it as an unsigned decimal number, you'd use U. If you want to print that same value as an octal number, you could print it, you could use a specifier O. Now remember, keep in mind, the computer stores everything as a pattern of ones and zeros. So it's not storing it in decimal or in octal, it's storing everything in binary, right? Everything is held in think about them as flip-flops or registers that are set or cleared, ones or zeros. Everything is just patterns of ones and zeros. A collection of those ones and zeros can be a data type int. You can print that int out in decimal. You can print it out in octal, in hex. You can print it out in lots of different ways. And these different specifiers allow you to do that. So you can print out something that's an int in octal. You can print it in hex by using %x or capital X, and that'll just give you lower or uppercase hexadecimal. And I'll show you an example of that. You print a floating point, and you can specify how many digits of precision. There's a format specifier for printing characters, strings, something called pointers. All right, let me show you some examples. So simple code here. Okay, the first thing is a character, right? And I'm defining a character called middle initial, and I'm giving it the name J. And then I have the next one is an array of characters. The way I've written this is how we declare an array. We'll talk about this on Wednesday, but this actually declares a string, which is an array of characters, and I gave it the value David. Okay, so last name is another array of characters, and I gave it the name McLaughlin. And then I have age in years is 59, and weight in pounds is 190.5 on a good day. Okay, and now what I'm going to do is, once I've sort of defined all those, I'm going to print them. Okay, so look at the print statement. Your name is, now first of all, /n just means new line. All right, it's just going to give us a new line. So it'll do a couple of new lines, then it'll print your name is, I have 3 format specifiers here, and then I have 3 variables. So it'll print a string. First name gets printed with %s, that's a string. Middle initial gets printed as a character. So S for string, C for character. And then the last one gets printed as another string. The next line, it says you are so many years old and your weight is so many pounds. Okay, %d is going to cause age in years to get printed as an int, and then weight in pounds gets printed as a float. Okay, so all we're doing is we're just making sure that the specifiers match up with the type of variable. And then when I show you the results, here it is. Okay, up top, I compile it, I run it. Your name is David J. McLaughlin, you're 59 years old, and your weight is 190.50000 pounds on a good day, okay? So that's just an example of how we can print print different data types. Now I want to talk about, whoops, let's see, let's go back to where we were. I want to talk about using different bases because this is important. So far, everything we've been sort of showing, all the values, the literals, the numbers have been base 10. And you know, base 10 uses the digits 0 through 9. Okay, I'm getting some questions here. Okay, can we use printf with %x for the project? Yes, you can. I'll say a little bit more about the project, but the answer is yes, and you can also see that answer on Piazza. Okay, we'll have occasion to work with hexadecimal. We'll work quite a bit with hexadecimal. That's base 16, and base 16 uses the digits 0 through 9, and then A, B, C, D, E, and F. Okay, base 8 is octal, 0 through 7. We won't use that. Base 2 then just uses the digits 0 and 1. And I know you've already seen this, and you've already sort of worked out, how can you sort of convert if you have a number like this, right? 1101 in base 2, you know that that's equal to 13 in decimal. If you have, a number like 123 in base 16, you know that you can convert that to 291 in decimal. And you've done that in ECE 124. The point I want to make here is if you just write down a number and you don't specify the base, then the default is that it's base 10. So if you see a number 291, you assume that's base 10 quite reasonably. If you see a number 123, that's base 10. All right. If you see 123 and then you see a little 16, then you say, okay, that's base 16. So that's how we know when we write something what base we want it to be represented in. And we do a similar thing in C. We have similar ways of representing numbers in different bases. If you just write down a number with no qualifier, it is assumed to be decimal, base 10. It'll default to base 10. If you have a number and you precede it by 0x or 0 capital X, then that means you're specifying a value in hexadecimal, base 16. If you preface it by O, that means it's a number in octal, right? And if you preface it by 0b, then it's in binary. Okay, so as examples down here I can, I'm declaring and initializing a variable x 3 different ways. First, I'm declaring it as a value in hexadecimal 0xFF. And FF corresponds to 255. And in each case, it's going to be, it has the same value. It gets represented by the same bit pattern in all 3 cases. But I'm specifying as the hexadecimal value FF, the base 10 value 255, or the binary value 1111, 1111. All of those correspond to decimal 255. Okay. You keep seeing me jumping back and forth in my slide. That's because what I'm trying to do is scroll to the bottom of chat to make sure I'm not missing anything. And sometimes when I do that, it's causing all my slides to jump. That's why you occasionally see that happening. Okay, let's go to slide 65. And here I'm just going to do some printing. I'm just going to specify some numbers in different bases, and then I'm going to print them. Okay, so what does this code do? It prints numbers in different bases. Okay, so here I'm declaring and initializing 3 variables, x, y, and z. X has value 127. That means decimal. Y has value 0x7f. Since I preface it with 0x, it means it's a hexadecimal literal that I'm typing in. And the third one, z, as 0b, and then a pattern of 1s and 0s. That means I'm specifying this in binary. They all get stored as patterns of 1s and 0s. Okay. Now, 127 base 10 is the same as 7f in hex is the same as 0, 1, 1, 1, 1, 1, 1, 1 in binary. So, but they all have the same value. So x, y, and z are all going to be represented in memory with the same pattern of 1s and 0s. But what I'm doing next is I'm just going to be printing them out. So I'm going to have one line, printf. Okay, x has the value. All right, I'm going to print x has the value. Something in base 10, something in base 16, another base 16, base 8. Okay, and so first I'm printing out that first variable as an int in base 10. Then the second one is going to be an int in base 16. The third one is also going to be an int in base 16, but the difference is I have lowercase x and uppercase x. You'll just see that the hex letters A through F are either lowercase or uppercase. And then the last one, I'll just print it in octal. Okay. And then I'm going to do the same thing with variable y and the same thing with variable z. And so when I go to the next slide and show you the result of this, here it is. Okay, x has the value 127 base 10, 7f base 16, 7f base 16, or 177 base 8. And then y and z also have the same values. Okay, so what's interesting, I think, about this example is I have declared and initialized 3 variables, x, y, and z, and I've initialized them, one of them with value 127 base 10, one of them with 7f base 16, which is equivalent to 127. And the third one, I expressed it in binary, but they all have the same, they're all equivalent. And then I was just showing you how we can take any of these values and we can print them in almost whatever base we want. So C has standard format specifiers to print things in base 10, 16, and 8. Curiously, C does not actually have a format specifier built in like this to print in base 2. And that's why I assign that as a homework assignment. Okay, so, you can use %D, %X, %O to print things in decimal, hexadecimal, or octal, respectively. But to print in binary, you got to build your own. So the assignment was write a program to prompt the user to accept the decimal number between 0 and 255, and then print it in either hex, octal, or binary.
Professor, we have a question.
Go ahead.
What is the benefit of using bases like hex and octal and hexadecimal versus binary?
What is the why would you care about this? Well, when I mean, you may not care about this if you, well, let me not say. Let me answer the question in the context of embedded systems. So if you sort of think back to the beginning of the class, the way an embedded system interacts with the world is through these ports. And each port is a series of pins that can be made high or low. And those pins correspond to bits in registers. So fundamentally, what that means is if we want to turn on an LED, or if we want to launch a rocket with a computer, ultimately, we're going to have a pin that we set high or low. High means turn on the LED or launch the rocket. Low means don't. For us to turn that on or off, we're going to have to put a 1 or a 0 into a particular bit position in a byte, in a register, in a variable somewhere. So we're going to get quite intimate with toggling bits high and low and dealing with integer bits all the time. And so that's going to be what we're doing in the rest of the class. Is a lot of things with 1s and 0s, reading bit positions and writing bit positions to cause things to read things in the external world and cause things to happen. So we're working with binary. Binary is very tedious and cumbersome to work with, because if I just go back and if you just look at this, how many 1s are in that? I mean, it's hard to even see it with your eye. It's 0, 1, 1, 1, 1, 1, 1, 1. I mean, it's challenging to look at it. 7F is easy to see. And so it's very easy, it's very simple to go back and forth between binary and hexadecimal. You just take the lowest nibble, that is the rightmost 4 bits, and that will correspond to 1 hex digit. The upper nibble, the uppermost 4 bits, that corresponds to another hex digit. So what we're going to find, the name of the game is making bits go high and low, to launch rocket ships and stuff. We're going to find it's too hard to work with binaries because we can't see them. So we'll be doing a lot of our work with hex. Octal, we won't be using. Decimal, we'll be using sometimes because the real world sort of thinks in decimal. So there's a sort of the example of why we would be doing things with decimal and then octal and then hexadecimal. Okay, I showed you printf. Now let me show you scanf. So scanf is formatted input when you're reading something from the keyboard. You can also read information from files. Now, in a traditional C course, you spend a lot of time on printf and scanf because there's an awful lot of interaction with the console, with the keyboard and the monitor. We're not going to spend a whole lot of time on scanf because we're not going to be doing a lot of input from keyboards and things like that with our embedded stuff, because they usually won't have keyboards. But I want to show you some of it because we'll have some occasion to do it. Okay, so scanf, like printf, is a library function. And so it's not actually part of the C language itself. It's a library function that is written and is compiled and is being made available as part of the standard C library. And the way it works is you just have a statement like this: scanf, and then there's a format specifier, and then thingx. And the first part of this is just like when we did printf. This is the format specifier. And so you would use %d if you wanted to scan some input into an int data type. You would use %f if you wanted to take some user input and dump it into a float. Likewise, if you wanted to take some input and dump it into a type char or type string, you would use these specifiers. So that's the first part of this. Okay, and what we're going to do with this command would do is it would allow the user to type something in, and the contents of that would then get stored in variable thing x according to that format specifier, whether it's D, F, C, or X. Now, what about this doohickey right here? Okay, what that is called the address of operator. And when we put that in front of a variable name, what we've done is we've created a pointer. And what this is doing is it's providing this function with the memory address of variable thing x. Okay, because thing x is a variable someplace in memory. If you want to get input from the keyboard and cause it to be dumped at that location in memory, you have to actually tell this function the memory location of variable thing x. And that's what that ampersand does. It tells this function the memory address of variable thing x. And that's why we have that there on this function. That will be made more clear, I believe, on Wednesday when we talk about pointers and functions in a little more detail. But let me just show you some examples. Okay. So this is a function that's just going to get the user's birth year from the keyboard and print their age on the screen. Okay, so int year of birth, and then I have a prompt. It's greetings. In what year were you born? Here's the scanf statement. I'm scanning from the keyboard. I'm taking an int, that's %d, and I'm going to cause that int from the keyboard to be stored at the memory location corresponding to variable year of birth. And then the next line, I just print that out. Okay. And, you know, when I print it out, you were born in year. Okay. We have a format specifier here, and that corresponds to the year of birth. Okay. And it'll say, and you are so many years old. It's going to print that as an int. And that's going to be the result of this expression. Current year minus year of birth. What is current year? I define that up top, all right, as one of these preprocessor directives, right? That way I can easily change that this year and next year and so forth. And then here's the running of the code down the bottom. Greetings, and what year were you born? 1962. Okay, you're born in 62 and you're 60 years old. Actually, not quite, because I haven't had my 60th birthday yet, but you get the idea. Okay, so in terms of keywords, you know, sort of going through the list, the ones in red are the ones that we've seen already. We've touched on them, even briefly. We've touched on them. And what I want to do is sort of keep plowing ahead as we just touch on more of these keywords. And once we've sort of seen them all, we can say, okay, we've at least had our quick look at the C language. So I'm going to actually switch to the next deck of slides here. And that will be, and you know, I realize that this is, well, I won't call it death by PowerPoint, but it's fatigue by PowerPoint, right? Okay, here we are, lecture 4, and just so you'll sort of see what we're doing here. This is a crash course in C. This crash course ends on Wednesday. We first sort of looked at just the structure of a C program. Okay, we looked at the structure. We just spent some time looking at these data types. That's where we are. And what I want to do now is talk about operators and relational operators. Then we'll get into things that I believe you've seen before, if statements, loops, and things like that. Okay, I'm going to skip this slide. These are the keywords we've already seen. And let's just talk about arithmetic operators. Okay, much of this is what you'd already expect. So we'll be seeing expressions that have an equal sign, plus, minus, times, divide, just what you expect. You've seen those before. There's also the modulo operator or the remainder operator, which you've seen, but it's a little less familiar. You know, 4 modulo 2 is 0, 4 modulo 3 is 1. It's just the remainder. Modulo is just giving you the remainder. So here are some examples of some expressions, some C statements that involve some of these arithmetic operators, all right? And I'll just dwell on the first, well, A equals B plus 50, that's sort of obvious, right? It's going to compute B plus 50 and set that result equal to A, so that the variable A gets allocated the result of B plus 50, all right? If you look at this third one down here, X equal X plus 1, right? Obviously, this is not a mathematical statement, right? Because, you know, what is equal to itself plus 1? That's inconsistent with mathematics, right? So clearly this is an assignment operator, right? I'm taking the value X and I'm replacing it with X plus 1. You call that the increment operator. We're incrementing X. And the reason why I show that one is there's a shorthand that all the cool kids use, X plus plus, right? X plus plus is shorthand for X equals X plus 1. Likewise, X minus minus is shorthand for X equals X minus 1. C has a lot of this. And I'm going to show you the next slide. There's a lot of stuff where C uses shorthand. And it's a little confusing initially, but once you get used to it, you'll see that it makes programming more compact, easier to read once you get it. These are all the shorthand operators. So I just showed you these, X plus plus and X minus minus. All right, look at this one. This is kind of funky looking. X plus equals 50. That's shorthand for X equals X plus 50. X minus equal A, shorthand for X equals X minus A. All right, and likewise for all these. X times equals A, X divided by equals A, X modulo equals A, right? X modulo equals A is just shorthand for X equals X modulo A. And so, you know, this is why initially you can look at a C program if you don't have this basics and you say, what the heck does this mean? And there's a lot of this kind of symbology in it. There are some variations on the shorthand increment and decrement. You can write y equals x plus plus, or you can write, let's look at this one here, y equals x plus plus, or y equals plus plus x. They both increment x, but one is called postfix and the other one is called prefix. We probably won't be using the prefix often, but just so you can appreciate the difference, if we just take the first one, y equals x plus plus, what that's doing is it's setting y equal to x, then it's setting x equals x plus 1. It's two different operations in one, right? Because x plus plus by itself accomplishes x equals x plus 1. If we say y equals x plus plus, this is a little tricky. We're saying y equals x, period, then x equals x plus 1. If we did it this way with the prefix increment, right? First we would, well, actually, I want to use this one here. I want to use this one. Sorry about that. So first we would increment x, then we would set y equal x. Okay, so it's just a matter of the order of which that we do these things. We won't actually use these a lot. We'll be using x plus plus sort of all the time, but y equals x plus plus, we'll have less occasion to use that. Okay, I want to do some simple math. I want you to be aware of what happens when we do simple math, when we have different data types. What happens when we're doing arithmetic between an int and a float? Okay. What happens when we do arithmetic with a couple of ints, and how is that different from a couple of floats? Okay. How do we print different data types? We sort of already saw that a little with the printf statement, but I'll show you some more here. Okay, this is a pretty dense slide, but what I'm going to do is I'm going to show you some quotients, right? And so I'm doing some dividing. And so what I'm going to do is I'm going to take a numerator and I'm going to divide that by a denominator, all right? Just the symbols, right? And that's going to be the quotient, okay? So that's just so you'll sort of get a sense of the language I'm using here. Quotient is the ratio, numerator and denominator, okay? So let's look up top. I'm declaring two ints, a numerator of 5 and a denominator of 2. And then a quotient, right, is the numerator divided by the denominator. What's the result? 5 divided by 2. It's an int. We have an int 5 We're dividing it by 2, 5, right? What's 5 divided by 2? It's 2.5. But that result gets stored in it as an int. So we throw away the decimal point. So since the quotient is an int, no decimal point, 5 divided by 2 is 2. Okay, just to give us a little bit of practice with modulo, 5 modulo 2, that's just the remainder, and that's equal to 1. Okay. Okay, now I'm going to show you some floats. So now we're keeping track of the floating point, all right? And notice that I'm deliberately, explicitly putting in a decimal point there, 2.0 and 5.0. And when I form the quotient, right, Q float is the quotient, the floating type quotient here is the floating type numerator divided by the denominator, 5.0 divided by 2.0, 2.5, good proper mathematics. We keep track of the decimal point. Okay, what about this one here? All right, so here I'm mixing. I'm taking the numerator, the floating point numerator, dividing by the floating point denominator, and I'm assigning that result to an int. So it's 5.0 divided by 2.0, that's 2.5. But I assign that to an int, so I throw away the decimal point, and I just get 2. Makes sense. Okay, the last two are a little tricky. There's what's called this is type conversion now. And so here's the rule. When you're doing arithmetic with different data types, the lower precision data type automatically gets converted to the higher precision data type. That's called an implicit type conversion. And here's an example. So I'm taking a numerator that's an int, dividing by a denominator that's a float. Okay, so here it is. I have 5 divided by 2.0. The rule here, this is called an implicit, implied type conversion. The 5 automatically gets converted to the data type of float, because I have an int, I have a mixed data types. I have an int and a float. The int is automatically converted to float, and then the calculation is done. That's called an implicit type conversion. It's just a rule of C. So 5 divided by 2.0 becomes 5.0 divided by 2.0. Result is 2.5. Another way I can do that is what's called an explicit type conversion. Okay, and here the way I've done it is I'm typing float and then n int divided by d float. What float n int does, float, if I put float in parentheses, it modifies n int and it temporarily converts that to a float. So whereas n int is 5, float modifying that becomes 5.0. I threw a lot at you here. I'm sort of showing you lots of simple quotients here, but the business of mixed types, implicit and explicit, it takes a bit for this to sink in. This becomes important to us next week, because on the one hand, we're going to be using ints a lot instead of floats. Why? They take up less space. On the other hand, we have to calculate things sometimes, right? Let's suppose you're trying to measure the temperature of something happening in the outside world. And if it's too high, you want to turn on a fan, or if it's a body temperature and it exceeds a certain value, you want to signal an alarm or something, right? Clearly, we're going to be running into these type conversion things, because if we had plenty of memory, we keep everything in float. Well, we wouldn't. There are good reasons to use ints in a lot of cases, but we're driven to use compact representations when we can. Float takes up a lot more space than int. It's a waste of space, and so we will encounter these kinds of things. I'll remind you about them again when we get there. Okay, this is just a screenshot of this compiler that I suggested that you look at. I just put it here so you'd see, what it looks like. You've got the URL up on top. I've been using this sort of quite a bit to try out code and to create demos to show you. I don't save anything here. You can go online and create an account with this online GDB. You can create an account that'll allow you to save your code if you want to. It's not what I'm doing. I'm saving everything on my computer, and then when I want to put something up here, I just cut and paste from Visual Studio Code. Okay, I'm going to show you the same thing, but I'm just going to blow it up on the next slide. There it is. Okay. And here I'm just showing you the results of some mixed integer conversions here. And let's just take a look at the output here, right? And I won't walk you through all the code, but we'll just sort of it'll be clear to us what's happening. I'm asking the user, please enter two integers separated by a space, and I typed in 5 and 2. All right, 5 and 2. Then it says the average of 5 and 2 is 3. But the average of 5 and 2 is not 3, it's 3.5. But obviously I'm doing something wrong here. I'm doing some integer division, right? Here I've got the average of 5 and 2 is 3.000. I did integer division and stored it as a float. And then the last two I got right, okay? You can look at the code later on to see what's actually happening. It's just an illustration of what I just showed you. And it just means you have to be a little careful when you're doing this because, you know, ints don't have their decimal point, okay? Next topic, relational operators. Okay, the idea behind a relational operator, this is simple, but it's got some little tricky implications, okay? We're going to use this to compare two operands. So I might compare two variables, A and B, right? These are two operands, right? Or I might compare one of the operands might be an expression like this, and I want to compare that against this. When we say compare, what do we mean? We're going to test to see if they're equal. We'll see if they're unequal, or we'll see if one is bigger than or less than the other. And so these are the kinds of expressions we're talking about, right? The first one is a test if A equals B. Notice double equal sign. Notice that. Equal sign. Notice the double equal sign. Notice that the equality test here is a double equal sign. Notice that the equality test is a double equal sign. Notice that the equality test is a double equal sign. Am I a broken record? I'm gonna open my mouth and say something. What am I going to say? I'm going to say, notice that the equality test is a double equal sign. Okay, I just want to drive that point home because it creates such a subtle error that drives some people really up a wall. You'll see what I mean later on. But what we're going to do is I can evaluate an expression A double equal B. If they're equal, this test will give me a 1 or a 0 as a result. If A is equal to B, I'll get a result of 1. For the next one, if A is not equal to B, I'll get a result of 1, and if they're equal to B, I'll get a 0. And let me show you some examples of this. Okay, if you look at the code, it's a little sort of different from things you might be used to. Look at that expression: int A equals 5 greater than 2. So what that says is I'm declaring A to be an integer. Its value is equal to 5 greater than 2. Right now, 5 greater than 2 is a relational expression. It's either true or false. If it's true, A will be 1. If it's false, A will be 0. The next one, int B equals 5 double equal 2. If 5 and 2 are equal, B will have a value of true, and it'll evaluate to 1. Otherwise, it'll evaluate to 0. Okay, and then look at, I've run it down here at the bottom. So look what happens when I run this. A equals 1, B equals 0, and C equals 0. So what we're doing is we're actually looking at the true falseness of these expressions to see whether they give us a 1 or a 0.
Professor, we have a question in the classroom.
Okay.
Is there a Boolean data type?
You can, there is a defined Boolean data type. It's one that we won't be using. Yeah, that is an actual, for our purposes, true is going to be any value other than 0. False will be equal to 0. Okay, and let me show you that. Let me show you that on the next slide here. This first part, what I wanted to do is just introduce the idea of these relational expressions. We're just comparing two different operands, and if the comparison is true, the result is 1. If the comparison is false, the result is 0. Okay, We can also,
Professor, we have another question.
go ahead.
If we use the library for Boolean, like, there is a C library that I imported in the lab.
Mm.
Like, is that okay? And for future projects, we import the Boolean library.
Were you able to hear that, Professor?
Yeah, can you repeat that question?
Yeah, so this student imported the Boolean library in C. Is it okay to use that if they already have it? And for future projects?
I guess if it's not okay, I'll let you know. All right.
And we had another question over there.
Yep.
Yeah.
So for this current lab that we're on, are we allowed to use %X and %O for offline X, or are we doing that?
Are they allowed to use %X and %O? And I believe this was answered on Piazza.
Yes, yes, you can, and go. Feel free to do that, and yeah, you and go and also check Piazza for that. Mhm. Okay. What I want to introduce here is logical operators. So here, this is the idea where we're taking the results of two different comparisons, like we just did, and we're combining them together with an AND function, right? So double ampersand means and, two vertical bars means or. Exclamation point means not. And so just to give you sort of a sense of this, this is just here we're just doing Boolean mathematics. 1 and 1 is 1. 1 and 10 is also 1. 10 and 0 is 0. Okay, why is it that 1 and 10 is 1? The way this works now, anything other than 0 is true. 0 is false. Okay. So looking at or 1 is 1, 1 or 0 is 1, 10 or 0 is 1. Okay, this is just another way of expressing things that you've seen before. And I'm going to show you an example where I make use of this. We don't have to look at the code because I do believe when I run it, it'll be sort of self-explanatory. It prompts the user, okay, give me an A, type in a value of A. I typed in 1, and it just says, okay, A is 1, not A is 0. A and 1 is 1, A and 0 is 0, A or 1 is 1, all right, A or 0 is 1. And then it just goes through and, I sort of repeat this. Suppose that I typed in A is 0, A is 0, not A is 1, okay, 0 and 1 is 0, 0 and 0 is 0, and so forth. And I just wanted you to see that if I use any value for A other than 0, right, they're all treated like 1 or true. 0 is treated as false. Any non-zero value is treated as true. Okay. Okay. The next sort of big chunk is control structures, and that's going to take a little while for us to set up. So I'm going to leave it at that, and we'll pick it up here on